All right. Turn this up. Okay. So, if there's any questions about stuff on the review or stuff on the homework, anything I can answer, questions about the exam itself, it's your time. I'd be happy to take any questions like that. So what can I do for you? What anxieties can I relieve? What mathematical mysteries can I resolve? Yep.
Can you go over the one on the midterm review number 4, which is like a sine squared?
Yes. Okay.
Plus k.
So that question. So let's talk about a strategy for a question like this. If you saw it. Okay. So you're looking at the series and you think, all right, we don't have a lot of tools that look like they work on this, right? I can't integrate it. I don't think a ratio test is going to help because of the sign that's running around in here. So instead, I'm going to remember that the reason that mathematicians and math professors specifically insert sines and cosines into problems is because they're bound to type 1, right? So the key observation about this is that sine squared trapped between 0 and 1. That's the central observation on this question. Okay? So with this observation, you can actually build out what the proper comparison for this should be. You can do this question with limit comparison, and you can do it with a comparison followed by a limit comparison, or you can just do it all in one go with a comparison test. So the way I would look at it would be, I would think, okay, well, since sine squared is less than or equal to 1, it would be really nice if I could get it, if I could just remove the sign. So I'm just going to say this is true. That's the trick with the signs, right? Since sine is less than 1, you can just imagine there's a 1 here, right? This thing times sine is less than this thing times 1 because sine is less than 1. Now, the strategy now is what can you say about this? And again, you can use the comparison test here, right? This is built so you can say, well, if I made the denominator, I mean, even at this point, you should be thinking this thing is like a 1 over k squared, right? That's what's really going on here is that this is like a 1 over k squared. But I have to make it into a 1 over k squared. This one was built so that you could notice that this denominator is bigger, so the fraction is smaller. So you could just say it's less than this. The denominator being bigger means that this is smaller than this guy. But that's just equal to 1 over k squared. Right? And that means that the terms of your series are smaller than the terms of a convergent P series. So the answer to the question after you did this calculation, you would say the series converges by comparison to 1 over k squared, and then somewhere you have to write that you know that that's a convergent P series. That would be the solution. That's the easiest solution to this, is to just say the terms of this series are smaller than the terms of that series. This converges, and so that also does. Okay. The other approach you could have taken that I saw people do is to say this thing is less than or equal to this, and then say this is about equal to 1 over k squared by the limit comparison test. So you could test this series by the limit comparison test with this one. So you could use limit comparison test to show this series forces that one to converge. And since this series converges, the comparison test would then tell you that that does. So limit comparison gets you that this converges, and comparison gets you that. If you don't actually want to, if you don't see this step right here with the inequality, you can still solve the problem just with the limit comparison test. Okay? All right. What else?
Number 5 on the homework.
Okay.
So the binomial one, and I don't know if it's right or wrong.
All right.
Mine is 7 over 6 plus x, or quantity 6 plus x cubed.
6 plus x cubed.
Just positive.
Positive 7. Okay, so this is 7 times 6 plus x to the minus 3. Put it in binomial form, but there's this 6 rate. So this is the homework 1110 number 5. Okay. So then the idea is that there's this 6 inside here, which is making this not work. So I'm actually going to take out a 6 to the third. Now, if you saw this on an exam, you won't, but like not this time, but like on an exam, what I would accept as an answer to this is this. Minus 3 to n over 6 to the n. I mean, this is an answer to this. You have to go one step further and put the n in there, but like I would just do this. Minus 3 x to the n over 6 to the n. Yep.
How do you put the -3 choose n in?
So that is so when you're doing in WebAssign, I'm going to point out that this actually simplifies algebraically. Right. So this pattern. So this is what WebAssign is actually looking for, just so you know, like how that notation doesn't seem like there's a way to do it easily in the WebAssign calculator, or people have had mixed success with like inputting it different ways. This pattern, if you actually think about what this sequence is doing, it goes -3, -4, -5 up to -3 plus n -1 over n factorial, right? That's what that means. Okay, so if you took all the negatives out, this is actually easier to show you what's going on with a concrete example. So let me show you what, like some terms, and I'll show you what the pattern turns into. -3 times -4 times -5 times -6 times -7 over 5 factorial. That's the fifth one, right? That gets you -1 times 3 times 4 times 5 times 6 times 7 over 1 times 2 times 3 times 4 times 5. These cancel with these. You have this 6 and 7 left over up top, and there's this alternating -1 that comes from how many minuses you piled in, right? So for n equals 5, you end up with n plus 1, n plus 2, 2 on the bottom, and a -1 to the end. So this simplifies to this algebraically. That's what WebAssign wants. WebAssign thinks that you did this step, where you determined that this form, if you write it out, you can find this pattern living inside of it. So then you just take that and you drop it into the series, and that's what you get. What else? Yep.
Number 12,
Which is
use the series to evaluate the limit
Okay.
as x goes to 0,
of
1 minus cosine of 3x, cosine 3x over 1 plus 3x minus e to 3x.
okay. So the whole point of this exercise is less the limit and more constructing new series from old series. The part that I want you to know how to deal with this is, let's actually see if we can write down what this is. 1 minus the cosine of 3x. Okay, well, cosine of x is equal to term by term. Cosine of x is equal to 1 minus x squared over 2 factorial plus x to the fourth, 4 factorial, and so on. That's cosine of x. So cosine of 3x is equal to 1 minus 3x squared over 2 factorial plus 3x to the fourth over 4 factorial. And then you substitute in, right? Okay. So what's 1 minus that? 1 minus 9x squared over 2 factorial plus 81x to the fourth over 4 factorial is equal to 1 minus 1 is 0. And then we have a negative applied to, so we have a 9x squared over 2 factorial and a minus 81x to the fourth over 4 factorial, and then other stuff. So this is the numerator of this fraction. This series right here is that numerator. On the bottom, well, 1 plus 3x minus e to the 3x can do the same thing. E to the 3x is equal to 1 plus 3x over 1 factorial plus 3x squared over 2 factorial plus 3x to the third over 3 factorial, and so on. So if you do 1 plus 3x minus that, minus 1 minus 3x minus 9x squared over 2 minus 81x to the third over 6. Well, the 1 and the 1 cancel, and the 3x and the 3x cancel. And you're left with minus 9x squared over 2 minus 81x to the third over 6, and so on. Okay. So what is our fraction now? The 9x squared over 2 on top, and a minus 9x squared over 2, and a minus 81x to the third over 6, and so on bottom. So the power series turned into these guys when you subtract. The point is that this kills the first term of this power series, and this kills the first 2 terms of that one. Yep. You notice anything about these? They don't cancel, but if you divide it by x squared, this has an x squared in it, this has an x squared in it, and so on. So you could divide the top of this by x squared. And you could divide the bottom of this by x squared. Like, as x goes to 0, the lead terms of this, the things that are controlling how fast it goes to 0, are this term and that one. So this thing, you can think of as being the limit as x goes to 0 of just divide everything by x squared. 9 over 2 minus 81 over 4 x squared plus dot, dot, dot. And on bottom, minus 9 over 2 minus 81 over 6x. If you take an x squared out of everything. What's the limit? Put in x equals 0, what's left? -1. 9 halves on top, minus 9 halves on bottom. All this stuff goes away. That's the limit. Make sense? Mm-hmm. All right. What else? That's not on the test. So in case people are worried that I'm going to ask you some complicated power series manipulation, I'm not going to put it on it. Yep.
Wait, are binomials at all?
I am not putting the binomial test. So the binomial series will not be present on the binomial series. It does. It was not on the sheet. I'm not doing the binomial series on the test. Okay. The binomial series, if that's going to come up, it's going to come up again maybe on a final when we have some more time to like process what it means to have those series. But I have so many ideas to test. I mean, you already saw even on the sheet I gave you. There's like 14 questions, right? That's too much. So I'm trying to restrict my attention to the things I really want you to know. And that's a very specific example. Now, these series, what is the step in here that I really care about? The step that I care about is that you knew what that was and you knew what that was. That's important, that you can see the cosine of 3x and the e to the 3x and write down their series without deriving it from scratch. Okay? That's what I want you to be able to do. So this step right here, you should be able to do that. Both in expanded form and sigma notation. What else? Yep.
Number 8, it was f of x equals 9 times the base of x, and then I wanted to turn that into 9 times 1/2 of 1 minus cosine 2x. So I like got to like the sigma notation, like turning cosine of 2x into that. But I didn't know how to like put in the 9 over 1.
Okay, so let's actually talk about. I'm going to do this term by term so you can see what's really going on when you do this. So what's really going on is one term of the power series is being deleted. That's what's actually happening here. But I'm going to show you that like it's easier to see what's happening if I expand it. Okay, so as we all know, we never work with sine squared or cosine squared. We just immediately substitute in the calculus formula. Right? Okay, so here's the slickest possible way to see what's happening here. If you write this as 9 halves minus 9 halves of this particular power series, and that's the step you should be able to do immediately, right? Okay, so here's the trick. There's a trick way to do this and there's an expansion way to do it. The trick way is to notice that if you put n equals 0 into this thing right here, what's the number that comes out? N equals 0 produces what number when you put it into that formula? 1, right? So I'm going to rewrite this as 9/2 minus 9/2 times 1 plus the sum from n equals 1 to infinity. I mean, after all, it's just a 1, right? I took literally one term out of the series and just started a different number. Okay, but what happens to this 1? This one touches the 9/2 and becomes a 9/2, but it's negative, but there's this positive 9/2 out here too. So where does it go? It goes away, it cancels. So this and this cancel each other. And what you're left with is just minus the sum from n equals 1 to infinity of minus 1 to the n, 2x to the 2n over 2n factorial. That calculation at the end, you just drop the first term, is what happens. Yep. Oh, yeah, sorry, it's supposed to be, yeah, that's my bad. There's supposed to be a 9/2 there, yeah. Like I didn't distribute the 9/2 to the sum, I should have done that. I mean, the reason that this works, another question you might have is, well, how is that always going to cancel? And the answer is yes, because the trig identity that's living underneath here is making that happen. Yep.
Are we gonna have to know how to shift it? And see?
No, because you can do, I'm doing this because I want to show you the slick way to write it down. The way I actually did this question when I did it was I just expanded the series and looked at what happened. So if I wrote 9/2 minus 9/2 of the sum for n, I wouldn't write it like this. I would write, okay, what's the series for the cosine of 2x? Well, it's 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial and so on. I would have written it like that without the sigma notation. Just expand it, but you get the same result, right? Because what you end up with is realizing, oh, there's this 9/2, but then you start distributing the 9/2 inside. Well, the negative 9/2 of the 1 becomes negative 9/2. And then the next step is to write plus 9/2 times 2x squared over 2 factorial minus 9/2 times 2x squared, 2x to the 4th over 4 factorial. You get the same answer, but without the sigma notation. You still get the fact that these cancel. And this is a perfectly valid answer to what we just wrote down. This is the right answer. It's a different form, but it's the same answer. That formula and this are the same. And if I ask you to do a question, you don't see how to do it in the sigma notation, you should feel free to do it in a series expansion. Even if I tell you to do it in sigma notation and you do it in the series expansion, you're still going to get most of the credit for the problem. Okay? Yep.
Wait, so, the first way you did it was the 1 come from.
Yeah, because what you're doing here is you're saying, okay, what does this pattern really mean? It means put in n equals 0, put that to the side, then add what you get when you put in n equals 1, then add what you get when you put in n equals 2. So this is all this is the n equals 0 term of that series.
Okay.
So you're always allowed to do that. I mean, this is a thing about series that you'll see more when you take this in differential equations, you'll see more that I can always do this. If I had a series that looked like this, I can just take out as many terms as I want and write them off to the side. I could put in 0 and get that, and I could put in 1 and get this. And then I just store the rest of the series inside with shifted, starting point. That's a legal move. It's the same object. Well,
So number 9 on the review.
sure.
Part B is asking to write a series of equations function,
Uh-huh.
1/x about a equals 3,
Yes.
and then find the power series for 1/x squared
Yep.
about a equals 3. I'm pretty sure I did the first part right.
Okay, so what you have is f of x. So you have f of x is 1/x about A is equal to
3.
3. Okay,
But then like being able to use that equation.
right, okay, so the basic idea here is that square that we drew, right? Where if I knew the series for, so why don't you tell me what you got for your answer for this? So you got that 1 over x is equal to what series?
N equals 0 to infinity, -1 n over 3 to the n plus 1
Okay,
times x minus 3 to the n.
perfect, okay, right. So you have that this function is equal to this series. Now, it asks you to find another series for f of x equal to 1 over x squared. So the relationship that you want to use here is the relationship of a derivative, right? But there's going to be a negative sign that's wrong. Because what is the derivative of 1 over x? D by dx here turns into what function? -1 over x squared. Right? So if you take the derivative of this power series, you don't get the series for this function, you get the series for that one. And then when you're done, you can multiply it by -1 to figure out the series for this function. So taking the derivative of this gets you this function, which means that if you took the derivative of the power series, which you shouldn't get overwhelmed by, because whenever you're taking derivatives of power series, it's just this thing that you're taking a derivative of, so just power rule. So the derivative here is, well, all this stuff was a constant, so it gets left alone. E to the n plus 1. And there's an n that comes and you lower the power by 1. That's just the power rule, right? N times the thing to the n minus 1. But that is the power series for this function. These things are equal to each other, but that's not this. So how do I fix it? I mean, that means that this thing is -1 over x squared, but I know the power series for that. You just put, I mean, literally all you're doing is you're taking the negative of this to get the function you want, right? So this square that you build, what you have to be careful of is the thing that you get the equality for is the derivative. It's not necessary. It could be a constant multiple of the thing that you were being asked to find. I mean, this is a -1 times the function you actually found with the differentiation. Okay. You can, yeah. So like the actual answer here is that, I mean, this turns out to be the sum of -1 to the n plus 1 and x minus 3 to the n minus 1 over 3n plus 1. Yeah, that's exactly what you do, right? You just multiply the -1, but then it piles into the other -1s. All you're doing is switching the order that the alternation happens. So on the homework, there were some issues because they gave you questions where taking the derivative put some number up here that wasn't in the function they were asking you about. And what you had to recognize when you got done was you just had to divide that number away. If there had been a 2 or a 3 here, and you were asked about this function, you just divide the series by 2 or 3 and you have the right answer. Okay. So this sort of differentiation square might not get you exactly what you want. But this is the way to keep track of the relationship. Well, where I start getting the question. I posted the solution for, my solution is pretty online that way. What else?
It's just a variation on this. It's like
Yeah, so if you were given, you mean like 10 over x? If I had 10 over x and I was doing it from the definition, I would just keep the 10 in.
Okay.
Right? What I'm saying is that if you had something like, suppose that you were just told, oh, 1 over x is equal to sum from n equals 0 to infinity, -1 to the n over 3 to the n plus 1 over x minus 3 to the n. And then I say find a series for 10 over x squared. Right? Find a series for that. Well, I'd still think, you know, that there's still almost a derivative relationship here, almost. So I would find a series for this guy because I could just take the derivative. So this function is equal to that. How can I modify it so I get a series for this one? Multiply by -10, right? If you take that series and you multiply -10, you're going to get a series for this guy. That makes sense, right? So it may be up to you to manipulate a series in a mild way. The derivative relationship might not give you exactly what you want, I guess. Yep.
On an exam, so we had like -1 here, we left it on the outside, is that valid or do we need to?
Oh, I don't care. I mean, the things that matter about putting in or taking out are the x's. Because if you have an x on the outside and I ask you to integrate a question, you can't integrate a product, right? X times a power series is not something you can integrate. You've got to put the x in to do the integration. And that's actually a question that would show up, say, in, like if I gave you something like integrate, the last question on the review actually is x squared sine of x squared, which is a good, this will illustrate the question you're asking. So one of the questions I asked on the review was to do this integral. The power series method, because that integral I think doesn't exist otherwise. And the idea here is that sine of x squared is actually pretty straightforward to write down a series for if you have memorized the power series for sine. Because the sine of x squared is, okay, test yourself. The sine, the odd powers or the even powers? The odd powers, the sine is an odd function. -1 to the n. X squared to the 2n plus 1 over 2n plus 1 factorial. That's sine of x squared. Don't forget that we had this x squared floating around out here, right? Don't get tricked into thinking that we're going to integrate this. That x squared must be incorporated into the sum if you're going to integrate this. It has to be. Because I can't integrate products. Can't do it. So what I've got now is the integral of x squared times this power series. It's 4n plus 2. Two times 2n plus 1 is 4n plus 2 is where that came from. I have to expand it out because I'm going to have to put this in the pile. That's the point. Okay, this cannot be integrated in this form. When you learn integral calculus, the reason we have all those methods is that products of functions can't be integrated. Very difficult to do that. So the point is you must put this in here with the other x's to do this question. So in this case, you do have to put it inside. So to proceed on the question, prior to integration, better have this written down. Got to get the x squared into the picture. Now, you very carefully don't get intimidated by this crazy looking integral because you remember all you're really integrating is that thing right there and everything else is a constant. So the power rule says add 1 to the power and divide by the new power. So this is just 1 to the n x to the 4n plus 5 over 4n plus 5 then plus 1 plus c. Okay. What else? Yeah. So like, I mean, I know that the book does it sometimes because it's giving you specific functions. I don't actually care. I mean, I don't care if you do that because like, we don't really have a way to recover. The thing is, we're not starting with a function we're finding a power series for. We're performing an operation. To find the c, I'd have to give you an initial condition. I don't really want to give you an initial condition. Like I don't like. What am I going to ask you to evaluate this power series and then set it equal to some number and solve for c? I mean, I guess I could tell you the value of the function is 0. Right? Oh, what is c if f of 0 is 2? What am I testing if I do that? Right? The fact that you can put 0 into x and know that it's equal to 0. So no, I'm not going to ask you initial value problem. You have your rest of your mathematical and scientific lives to answer questions where everything is applied and you must always find all constants. For now, we should just appreciate the grace of the arbitrary constant. What else? Okay, how about this? What if I said, go using power series. That d by dx is e to the x is e to the x. Big deep question. It is. Look at it. After all, no one ever proved that to you. They just asserted it. Oh, e to the x is a function that has that property. Why should you believe that? So the property comes from the definition of e to the x as the particular power series, right? E to the x is defined as this power series. Very carefully defined as this power series. So how would you do this question? It's like give up before you start. It's not allowed. You can't do that. Well, what do I have to do to that power series to prove this? Take the derivative. Do you think it's going to be easier to see what's going on here if I do it in sigma notation or if I do it expanded? I think the expanded form might actually be easier because I can do some algebra. When we're done, I'll show you how to do it with sigma notation. Okay. So this question, this is actually a question I could ask on an exam, a question like this, because it uses ideas you know, and it's pretty straightforward. It's not a question that is like a terribly difficult question, but it requires that you think about what I mean about showing a function of the power series. I'm trying to show that the power series for the derivative of e is the same as the series for e. So I'm actually going to calculate the derivative of the power series for e. Notice that what's being tested here is, do you know the series for e? You know it, and then can you differentiate it? Okay, so you compute this derivative, and what do you get? Derivative of 1 is 0. I mean, it's nice to put that 0 in there so that your poor, long-suffering math professor knows that you took the derivative of 1. You don't need to, but sometimes it's not a bad idea to show me that you did that. Derivative of x is 1. The derivative of x squared over 2 is 2x to the first over 2 factorial. This is 3 times x to the second over 3 factorial. 4 times x to the third over 4 factorial, and so on. There's the derivative. You haven't really finished the problem yet because you took the derivative correctly. You still haven't showed me that this is the series for e to the x. So another thing I might be looking to test is, do you understand how to manipulate factorial expression? 2 divided by 2 factorial, 3 divided by 3 factorial, 4 divided by 4 factorial, 4 divided by 4 factorial, 1 over 3 factorial. Right? The last number in the list cancels. That always happens. So this is 1 plus x squared over 2 factorial plus x to the third over 3 factorial. Oh, this is why we picked this as the power series for e to the x. Because it algebraically perfectly cancels when we take its derivative. But this is an illustration of the fact that when you take the derivative of e to the x, you get e to the x back again. This is the series for e to the x. This is just e to the x again. It's what you wrote down right there, right? There it is once, and there it is again. You wrote the same series twice. Yep. Notice I did not show you the sigma notation at all, so I didn't have to deal with that. Right? I did this term by term, so I did not have to tell you anything about the ends. So that this particular thing, if you get a question like this and you don't immediately see how to do it from the sigma notation, write it term by term. Point of this example is, don't get trapped in trying to wiggle that thing around and force it to happen. You can't see how to proceed, write it term by term. And yeah, sort of, I think, explicate why we chose this to be the definition of E and why E is so special. It's the only power series that has this property. You need the powers to come down and perfectly cancel those factorials for this to happen. Okay, so with sigma notation, this is a harder question. I'll show you what would happen if you did it the other way. If you took the derivative of the sum from n equals 1 to infinity, sorry, 0 to infinity of x to the n over n factorial, the power rule says, This is the derivative of E. This is also a legitimate solution I'm going to write down right now. This is equal to the sum from n equals 1 to infinity of n x to the n minus 1 over n factorial. But now abstractly, you need to recognize that n over n factorial is 1 over n minus 1 factorial. That's the thing that's, I think, obvious here in a way that's not necessarily here. N over n factorial is the same as n divided by 1 times 2 times n minus 1 times n. And that cancels with this and leaves behind 1 over n minus 1 factorial. N over n factorial is 1 over n minus 1 factorial. Doesn't look like E. So I gotta go. Now you were talking about the indexes, right? This is where you have to recognize that this series could be started at a different number and I have to balance it by changing these numbers. Right? So this is called an index shift, which is not part of what we're doing in this class, but you will have to do it in later classes. That's why I didn't teach it this way. This series is the same as this one. Because if you put a 1 in here, the first term that comes out is x to the 0 over 0 factorial. And if you put a 2 in, the next one is x to the first over 1 factorial. The terms of this series and the terms of this series are the same. This is called an index shift. You are more than welcome to do it this way if you want. I encourage you not to get buried in the sigma notation if you don't see it immediately. You're completely valid working term by term in a problem like this. If that makes sense. But I did it this way to point out, like, if you do it this way, this is valid. Yep.
So when you took the derivative of the sigma notation, why did you change n equals 0 to n equals 1?
So that is a convention of convenience, because if you put n equals 0 into this, what it's supposed to represent is that when you take a derivative of a polynomial, you get one less term. So if you took the derivative of just 1 plus x squared, you would get x plus, 1 plus 2x. You went from 3 terms to 2 terms. So we've dropped a term, which is why we cut one term out. But you should notice that even if you put 0 in here, this is still defined. And a 0 comes out of this formula if you put 0 into it. So one of the more obnoxious facts about these series is that this x to the n minus 1 over n factorial. That series is equal to this one. Because this starts with 0. So I could start it at 0 or I could start it at 1, it doesn't matter. Which is annoying. So the one version of it I really want you to know is the n equals 1 version, because then this manipulation is very easy to do. Otherwise, you have to realize, oh, there's a 0 stuck on the front of this I can just get rid of. So why not start the series for the first non-zero term? Yep.
Is the first group, it's
Yeah, but the thing is, we do that by putting the plus c on the outside. So we never increase the set of indices. We just stick the plus c on the outside, and it actually turns out to be the case that that's actually. So generally, what the plus c is in a question is it's f of whatever the a is for the particular power series that you're working on. So in this case, it would be whatever the f of 0 value is.
Okay.
So when you're finished, you can lump it back into the Taylor series sometimes, but sometimes not. It may not fit the pattern. Tell me how to approach this question. As I do that with power series, what's the approach? How are you going to do that? So we're going to think about this as being the integral of x cubed times something that looks like the geometric series. The reason that you make that move, so the hard part about this question is identifying that you can take the x cubed off and get something out that you can do with a series that you're supposed to know. So it's sort of a second order question because you have to make a manipulation to get the easy thing out, right? But then this thing, you have to also be able to turn that into a series. What would you do to do that? Minus minus. So yeah, let's uncancel things. Since we're sophisticated mathematicals or mathematicians, we uncancel things. All right, now why am I doing this question? Because there's a warning I want to put here. That thing right there, you have to be really careful about distributing that n inside. In this case, it doesn't matter, but normally when you integrate something with an n in it, it very much matters that the x is by itself. If you're going to work with a series, this is a correct series for this function. It is. This is correct. This series is this function, but you can't integrate it because this n is outside of the x. X is all wrapped up in some function. If you want to integrate this, you should write it in this form. Like you don't even need to separate out the -2 if you don't want. You can just leave that. But this is the form you want in for differentiation, exponentiation. Get the x by itself. Of course, that's not the answer because there's x cubed going around. So warning 2. After you get all excited because you found a power series, hell yeah, I found this power series. I'm going to do it. I'm going to integrate that thing, but then you forget to put the x cubed back in. Happens all the time. Don't forget to put the pieces back together again. What you found was a series for that part. So really what you're integrating here is x cubed times the sum. Because the integral, don't get tempted until you integrate it. So you've got the sum by itself, minus 2 to the n, x to the n plus 3. And that thing you can integrate. You've got x all by itself. There's only one of them. There's no product anymore. It's some giant polynomial. The answer to this question, minus 2 to the n, x to the n plus 4 over n plus 4 plus c. Okay, get everything together first. Well, yep.
So on this one with this, with the number under the sigma also.
It's in this case, because you're integrating, it stays, you have it, so when you integrate, you create a constant, you don't destroy one. So all of these are still there when you're done integrating, right? When you integrate a polynomial, you keep everything you already had plus an additional thing. So these indices don't change. When you integrate, you don't lose anything. So you keep the same index. You just get this extra plus c outside.
So what's the polynomial when we do change?
You're gonna drop the index if you differentiate. And the more times you differentiate, the more times you have to take terms off.
Okay.
What is confusing?
Oh, just, I was confused when you were integrating the x, and stuff after, and you wrote it like on plane, so I'm actually.
Oh,
But then I.
okay. All right. I got 5 minutes left. You guys can ask me another question before you go home and work on other classes until tomorrow morning. What else?
How do we solve that integral once we have the power, once we have the sigma?
With this integral? Well, precisely like this, right? So you mean this integral right here?
Integral there at the top.
So, but this integral, okay, so that integral right there is this. This is that integral.
All right.
Because, so what did we, let's actually put all the pieces together and see what we actually did here. We started with this. And we rewrote it as that, so this guy right here is that function, right? That's what all of this derivation was, so that we got that series to replace this function. So minus 2 to the n, x to the n plus 3. This is this function. So this integration just, once you have it written as a power series, you can go inside and just integrate this. And so the final step is the minus 2 to the n, x to the n plus 4, n plus 4 plus 8. The derivation was to get to the point where I could replace this function with its power series. Then then you're just done. Yep. Sure. Yeah. About I can do one from the sheet if you want. Was the t over 1 plus t cubed, I think? Like one of those, more integration? Okay. More power series. You want, okay, what kind of power series? Literally anything. All right. How about
Here's something that's likely to be on.
well, something likely to be on the test? Yes. Okay. All right, how about derive a power series? That's a good exercise, right? Let's derive a power series. Let's derive the power series for e to the 2x at x is equal to 1. Right? We're just going to derive a power series from the definition. We haven't done that yet in here, so let's do one. Okay, so f is e to the 2x, f prime. So, okay, let me give you a guide here, which is if you're computing a power series from the definition, if you're not going to try to find the sigma notation for what you're doing, at the very least, you should give me enough terms so I see you recognize the pattern. So saying, oh, I'm working term by term and then writing down 2 derivatives is probably not enough, right? Give me like 4 or 5 terms if you're going to do that. I'll specify in the question how many terms I want. F prime is 2e to the 2x. F double prime is 4, let's be more careful, 2 squared e to the 2x. F triple prime is 2 to the 3rd e to the 2x. I'm going to need some derivatives, right? Now I got to evaluate them at the center of the power series. So f of 1 is e squared. F of 2 is 2 to the 1st e squared. Notice I'm being very careful not to simplify away patterns when I'm doing this. I don't want to lose the patterns. That's not f of 2, it's f prime of 1. This is f double prime of 1, which is 2 squared e squared. F triple prime of 1 is 2 to the 3rd e squared. I bet I know what the nth derivative of f is now. I bet I do. I bet the nth derivative of f at 1 is 2 to the n e squared. That's what that pattern looks like to me. So now I just need to remember what the formula for a Taylor series is. How do I write that down? I can work term by term, or I can work like this. To the end. And just plug in your formula. You got this. Sum from n equals 0 to infinity of 2 to the n e squared x minus 1 to the n over n factorial. And now you've got a Taylor series all ready to go. How would you find its radius of convergence? Besides guess. Use a ratio test to do it, right? The ratio test is very easy to check this thing with. So if you wanted an R for this thing, you would test the limits, then goes to infinity of the an term, which is 2 to the n plus 1, e squared, x minus 1 to the n plus 1, over n plus 1, factorial times n factorial, 2 to the n, e squared, x minus 1 to the n, blah. And when you're all done with this, there's a 2, there's an x, there's an e, but all of this ends up turning into this. You get an x minus 1 is left over, and there's a 2, and there's an e squared, and you have a limit as n goes to infinity of 1 over n plus 1, and that's 0. When you do once all the algebra here and all the cancellation is finished, you're going to get a limit that is 0. Limit being 0 means every single value of x produces something less than 1. When you get the limit is 0, that means r is infinity. All right, now you are, and ask me questions if you got them. Like, I'll be on Slack, send me emails.
Okay, 2 quick questions. So I'm a little confused as to why the Taylor series is x minus 1.
Because it's always, the idea is that this value, I should be able to plug in here and make 0. Right. So if I want the series to be centered at 1, I need to do, this is really what's happening when you're doing the translation from the right by 1.
Correct.
Translation to the right means that you have to subtract. Remember like x minus a means the right shift?
Well, X is greater than 1, so
Yes, and if it was negative one, it would be x plus one here because it's shifting to the left instead of the right.
okay, that makes sense. I thought that was like. I didn't say questions. I get that wrong. Or review packet.
Oh, no, this is the Fire Solution Challenge. No, that's, it's on the Canvas page. I'm sorry, I don't have a physical copy.
Okay, I think it might not be up there.
Let me check.
I look for it now.
Module.
Making sure it's correct.
Right there, top of the module page.
I thought that just went. Oh, never mind. Okay.
Yeah, it should just be, the questions are embedded in the topics.
Okay, I thought it
I'm
was. a
sorry,
separate
no, it's all stitched together because I put the questions in with. When you're doing a review, I think it's important to have the questions tied to the topics that they're
Right.
connected to, right? So yeah, no, it's all together.
Okay, cool. Thank you.
Yep.
Like we made this part in the workshop. but
Yep.
I remember also making the grading test. If it says like not completion, does that mean you just change the test or does it like?
Yeah.
Okay, so they don't, okay.
Alright, what is the exact date?
Tomorrow.
I think you know, like, beginning of the quarter, but, I'm on the.
Yeah.
So,
Yeah, I mean, those dates have been posted since
Yeah.
since the very beginning.
Oh.
They're on the course calendar.
For some reason, I thought it was today. But,
Well, I guess that would have been terrifying. No, yeah, tomorrow.
yeah, got it. Thank you.
Okay. You got me taking it in this.
Yeah, if that's what you prefer.
Yeah.
Yeah.
Yeah. just
Yep.
making sure.
Yep.
Okay, cool.
That's a lot.
Chill, it's all right.
No, because I go straight from like physics and then I have to come into this and then it's like. It's a lot.
Yes. No.
No, I fixed
You
that.
gotta have, you gotta have a.
I'm like, chill. I'm missing my classes.